Hello all, welcome to the last session of Nyquist plot. In this session, we are going to solve a problem on Nyquist plot. We will just see how from a given open loop transfer function, a Nyquist plot is sketched. Then the Nyquist criteria is checked whether it is getting satisfied or not. If yes, we will comment that the system is stable. If not, the system is unstable. Now let us look at the problem at hand. Yeah. So this is the open loop transfer function given to us. GSHS is equal to 5 upon S into S plus 1 into S plus 2. Now let me give you the intuition exactly what we are going to do. From the given GSHS, we know that we need to have three parameters Z, P as well as N. And from the Nyquist criteria, we have seen that N is the encirclements around the critical point, which we will obtain after sketching the Nyquist plot, because N are the encirclements made by mapped contour, right? So N we will calculate in the end. We have Z and P. Z is nothing but number of zeros encircled by a Nyquist contour. We know that the Nyquist contour that we assume to be the right half of S-plane in the semicircular manner by skipping the poles, if at all there are any poles, on the imaginary axis. So now let us start with the solution. Initially, we need to find whether there are poles or zeros in right hand side of S-plane. Okay, so from the given transfer function, we know that the poles are at 0, then at -1 and at -2. So out of these three poles, there is no pole which lies in the right half of S-plane. Please understand, we are analyzing open loop transfer function to comment on closed loop stability, right? So out of these three, no pole lies in the right half of S-plane, and that is why we conclude that P is equal to 0. There are no zeros, so Z is automatically equal to 0. Now, from the Nyquist criteria, if you remember, N is equal to Z minus P, or zeros have to be 0. So we have the Nyquist, modified Nyquist criteria is equal to N is equal to minus P. So in the end, we will see how many encirclements are there around the critical point, and that has to be equal to minus P. In this particular case, the value of P is 0. So we know that for the system to be stable, the value of N has to be 0. That means there are 0 encirclements around the critical point. Okay. So now the next step would be to decide upon the Nyquist contour. We know that the right hand side of S-plane is assumed to be Nyquist contour, and we need to skip the singularities. So this is the Nyquist contour in front of us. Okay. This Nyquist contour, if you observe that, will skip the pole at origin, and so we have a smaller semicircle here by skipping the pole at origin, right? Then we have 4 sections that we have named. This section is C1. Please understand, C1 section is known as section 0 plus up to infinity, plus infinity, right? Section 2, that is C2, will be this semicircle, okay, with R as the radius, but R tends to infinity, and the R e raised to j theta is the representation of the magnitude and angle, and theta will vary from plus pi by 2 to minus pi by 2 as the direction is clockwise. That we have seen in the last session as well. Then we have section C3. Section C3 would be minus infinity to 0 minus. Now what this 0 plus or 0 minus is? We are assuming the radius of the smaller semicircle to be very small, so that we can take the limit epsilon tends to 0. And so that is why just skipping a single point, we denote the upper portion, upper point to be 0 plus and lower point to be 0 minus. Now after marking these sections, now we need to sketch the Nyquist plot for each section independently, and then we will form the whole Nyquist plot. So we will see how to sketch the Nyquist plots independently. Nyquist plot basically is nothing but a polar plot. So method of sketching the Nyquist plot section wise remains the same as we do for polar plot. So suppose now initially we consider the section to be C1, for which we will be calculating the magnitude as well as the angle. So section C1 would be 0 plus to infinity, right? So this is the section, straight line. Now for this section, the magnitude calculation is by substituting S is equal to j omega. All of this method remains the same. Please remember this, right? So j omega, h j omega comes out to be 5 upon j omega into j omega plus 1 into j omega plus 2. Just substitute j omega in the place of S. Now its magnitude comes out to be 5 upon omega into bracket under root omega square plus 1 into another bracket omega square plus 4, just by taking the magnitude from this term as well as this term. So this is the magnitude of the transfer function, and this is the angle. Angle for this factor would be minus 90 degrees. Now again, the knowledge that we gained while learning the Bode plot comes to our support. So minus 90 degrees for this particular factor. Then for this factor, the angle has to be negative because the factor is in the denominator, right? Sorry about this. Yeah. So the factor is in the denominator and the angle to be tan inverse of omega. Then another factor would be minus, again, the same factor in the denominator, tan inverse of omega by 2. So this gives you the phase of the system. Now what we are supposed to do for this particular section, this magnitude and phase equations we are going to use for all the sections, but now for section C1, limit of omega is from 0 plus to infinity, right? So first we will substitute 0 here, we will get the magnitude, then we will substitute infinity, we will get the another magnitude. These two values are limiting values of the magnitude that we have, and corresponding gain also we can calculate by substituting two different values of omega here, first 0 and then infinity. Now let us start with the calculation for section C1 rather. Okay. Now repetitively I need to put this slide, otherwise we will have to remember exactly which section belongs to which part, right? So this is the section C1, and you can see that section C3 is nothing but similar to section C1 on the other side of real axis. So whatever Nyquist plot or polar plot we get for section C1, for C3 we are going to get mirror image of that. Okay. Now, okay. So now we substitute omega to be 0. It gives you the magnitude as infinity. You can substitute and check whether these values are right or wrong. You just can verify these values. I have written it from the equations. Okay. And angle comes out to be minus 90 degrees. For omega equal to infinity, magnitude becomes 0 and the angle is minus 270 degrees. So now for section C1, the polar plot that we have has limiting values of magnitude as infinity and 0. Our polar plot starts at magnitude infinity, because for omega equal to 0 we get the magnitude as infinity, and for omega equal to infinity we get the value 0. So this is the last value that we have for this particular section. And where should it start? It should start from minus 270 degrees. Sorry. It should start from minus 90 degrees and then it comes out at the end, comes to the end at minus 270 degrees. Okay. So now check out this section. Now this is the conventional way of drawing it. Please understand, these are the rough sketches. Whatever we assume as the scale, irrespective of that scale, we are sketching it just by considering the limiting values. Okay. So this starts at infinity. So it will start at infinity and then it will end at 0. Now where will it end? Start at minus 90 degrees. So it will start at this line. Okay. So on this line at infinity, it will start, and on minus 270 degrees. So this is minus 90, minus 180, minus 270, right? So on this particular line where the angle is minus 270 degrees, it will end. And that is why the section C1 polar plot can be sketched in this way, right? Similarly, as we have discussed earlier, section C3 will be mirror image of section C1. Please consider the direction also. Okay, so this polar plot is for section C1. This one is for section C3. Now let us go to the next section, which is section C2. Okay, now so section 2 is the larger semicircle consisting of complete right half of S plane. Okay. Now the magnitude is R e raised to j theta. So for section C2, substitute R is equal to, sorry, S is equal to R e raised to j theta. Just give me a minute. Okay. So S is equal to R e raised to j theta. In the magnitude equation, we can just substitute this. Instead of S is equal to j omega, now we are substituting S is equal to R e raised to j theta. Okay. And now, if you can see this here, by taking R e raised to j theta common from these two columns, these two brackets, we get R cube, because already there is this term and you keep on multiplying with these two terms. So we get R cube e raised to j 3 theta. We are converting it into standard time constant format. Okay. So now if you consider this 5 upon R cube, okay, R tends to infinity. And that is why 5 upon R cube is going to be very small. So we can consider as epsilon. Okay. And so by taking this term, this e raised to j 3 theta term in the numerator, we get the negative sign. Okay. Now the angle for the section C2 would be plus pi by 2 to minus pi by 2. If you look at the section C2, considering the direction. Okay. Now when you substitute plus pi by 2 and minus pi by 2, we get the angles. And so section C2 maps to a circle of radius 0. Now why radius 0? Because the magnitude comes out to be 0, or rather very small. Okay. So the complete section C2 is represented by a point at the origin. Okay. Now similarly, section C4. Now section C4 is the smaller semicircle where the radius is epsilon, which tends to 0. Again, substitute S is equal to epsilon e raised to j theta depending on the radius. After substituting, we get 5 upon epsilon e raised to j theta, then two different brackets after substitution, and then again we do the same thing. Again, the 5 upon epsilon, after taking these two common, again we get epsilon raised to 3, right? So that step is skipped on the slide, but you can very well understand.